Guten Morgen. Bonjour.
Bonjour.
Yeah, sure.
All right, so welcome to this special webinar today. I'm Andy, I'm your technical host for today. I will make sure that the session is recorded and that you will receive all the follow-up emails with the right recordings and documents that have been shared with me. But with this, without spending more time with me, I will hand over directly to Peter, who will tell you more about what's happening in the next coming 60 minutes. 60 minutes,
60 minutes, 60 at least. Andy, Dankeschön. Thank you very much. Guten Tag. Hello, everybody. Thank you for joining us today. As you may know, just from registering for this webinar, we are personally all very excited about it to welcome our distinguished guest speakers from SABIC Specialties. SABIC Specialties, one of the largest plastics manufacturers in the world, very much trying to be part of the solution and not part of the problem when it comes to plastics. We have been engaged with SABIC now for over 4 years, primarily around the topic of CAE simulation material data. In our case, related to injection molding simulation, but we are also in discussions about getting SABIC material properties in the future for structural analysis, as an example. So there's many different things that we can do with SABIC. I had the very good fortune to be invited to and hosted at SABIC's Technical Innovation Center in Bangalore, India, just a couple of years ago, where they showed me some of the most sophisticated material testing laboratories in the world, as well as one of the most sophisticated injection molding research laboratories in the world, where these guys have live injection molding machines, I would say instrumented in every way possible. So they are basically measuring every pressure, every temperature, every time, every velocity that they can at the injection molding machine. And what was born out of that was a real-world validation study where basically SABIC gives us all of the material data, the injection molding process parameters, and the model that we need to simulate. We run all of that through our software and make the correlations between the real world and the simulation. But before we get into any of that, I would like to introduce Subhranshu Mohapatra. Subhranshu is leading this team in India. So Subhranshu will give you a brief introduction to what they're doing at SABIC, as well as a brief introduction to his team, and then we'll get to take a more in-depth look at what SABIC is doing in terms of this injection molding validation and material testing. So Subhranshu, if you can hear me, please feel free to unmute yourself and take it away.
Thank you, Peter. Thank you, Peter, and welcome one and all to this live webinar. We are streaming live from the state-of-the-art injection molding lab here at the SABIC Technology Center, Bangalore. With me, I have my colleagues Aditi and Ashwin, and over the next 25 minutes or so, we'll be taking you to the cutting-edge work that we do to make sure the data that you get from us is thoroughly generated, checked, cleaned, and validated. But before we start, I would like to give you a quick introduction about SABIC. SABIC is headquartered out of Saudi Arabia. We are a almost 50 years old company, and we operate in 50 countries worldwide. We are the #2 company in the chemical sector as per the brand value, and we are a very innovative company. We have more than 10,000 patents, global patents that we have filed and in the process of application. And we have 66 world-class plants worldwide where we generate almost 150 products every year to meet our customer needs. Within SABIC, we have 4 main business verticals, and the vertical that we belong to is known as the SABIC Specialty business. This business is dealing with the high end of the resins, additives, and compounds. We have products like Ultem and Noryl resins and LNP compounds. In the specialty business, we have a very clear and focused strategy to really serve our customers' data needs. The strategy is very simple in terms of, like we want our customers really to succeed with their applications and our materials. And how do you do that with our data? Is by improving the access and trust in our data. So we have three clear strategic pillars to achieve this. One is to have the right system, to have the right content in the system, and have the right operational excellence. For example, for the right system, we have a very state-of-the-art database which is called as the Metal Finder, which is accessible to all of you 24/7 through our website, where you can find all the type of data, and in this data is generated very thoroughly by the different by the lab that we have here in the Bangalore. This data spans all different property types and carefully generated with the latest test standards, and it's thoroughly checked and validated even at the application level. And as far as the operational excellence is concerned, we have a very well-equipped lab with very highly experienced experts who go through a very well-documented operating procedures to make sure the data that you get is good for your simulations. As far as the Metal Finder is concerned, I would like to tell you a few quick things about it. It is for you, it's one-stop shop to find out the right materials for your applications from our portfolio. So this Metal Finder can help you to quickly search and find the materials using a lot of different types of easy to use search filters. You can also use a free text field to find the materials, and once you get the materials, you can also find out what are the different use cases that is possible with our materials. I would recommend that you register on this tool to get more out of this portal. Once you register in the tool, you can get access to multi-point material data and the CA cards, so that you can confidently do the simulations. In addition to that, you can also get molding guides, design guides, and secondary operation guides. And this tool is available on our website sabic.com. You can go to the product tabs, and also you can type directly the URL that is shown on the screen, or you can scan the QR code. It's called metalfinder.sabic-specialties.com. So with this, I will pass it on to Aditi, who will take you through the detailed metal characterization that we do to make sure the data that you get is of right quality. Aditi, over to you.
Thank you, Subhranshu. Very nice.
So hi, my name is Aditi, and I'll be taking you through the material data considerations. We all know that rheology is a very important property when we do injection molding, pressure predictions, and simulations, and the actual injection molding process. So I'll take you through those aspects. So I'm talking about why do we need viscosity developments for accurate CAE simulations. We have a graph of pressure and time, and we know that the blue curve here, it represents the actual injection molding pressure that is experienced inside the injection molding machine in the cavity. And the orange curve, this represents the CAE simulated or the predicted injection pressures. We see that there is a gap between the actual injection molding pressure and the CAE predicted values by a delta of about 30%. So we need to address this issue in order to give a better prediction to our customers and enable them to have a better way of characterizing the injection molding pressures. So what is our goal? Our goal is that the CAE predicted pressures should be a very close match with the actual injection molding pressures which are experienced inside the cavity. So we have devised a method, and we know what kind of parameters will influence this. So we have come up with a methodology to show that how we can bridge this gap between the actual injection molding pressure and the CAE simulations. So the question arises that where these things are important. So when we have newer applications which require pressures of about greater than 100 MPa, which is not conventional, where there is a reduced wall thickness, a highly filled system, or maybe large and complex parts, we need this kind of methodologies to bridge the gap between injection molding simulation and the actual injection molding process. So there is an analytical method which is available wherein we characterize the parameter of pressure dependency, which is also known as D3 parameter, which is a parameter of the cross WLF model widely used in the injection molding simulation softwares. So it is very important to know the pressure sensitivity of the polymer melt viscosity, and this is required for an accurate CAE simulation, and we need to understand this for the high pressure injection molding processes. So I will be covering the method to determine the D3 parameter in this webinar, and it is done by combining rheological techniques like the dynamic technique as well as the capillary rheometer technique. When both these techniques are combined, we can measure the D3 parameter. So what does the dynamic data contribute? So dynamic data contributes to 6 out of the 7 parameters of the cross WLF model, and we need to have the 7th parameter, which is D3. So how do we go about that? So D3 is determination is done with the help of a capillary rheometer, which is fitted with a counter pressure cell, and this measurement is carried out so that we know the pressure dependence or the influence of pressure on the polymer melt viscosity. The cross WLF parameters are validated then with the help of injection molding process with the help of a box tool, which will be covered by my colleague Ashwin, and then the results between the actual molding and the CAE simulations are compared. So a comprehensive rheological characterization is required in order to understand the influence of not only shear rate and temperature, but pressure on injection molding. So the cross WLF model, which is widely used in simulation, is only because of its simplicity, and it also tells us, what does D3 parameter tell us? It tells us about the influence or the changes in glass transition temperature due to the applied pressure and the increased melt viscosity. So in most material data cards that you will encounter or see, you will find that the D3 parameter is either missing or it is not evaluated at all. So how can we account for this D3? So when we measure D3 and when we give this material data into our material card, so what all we could avoid? So we could avoid that the customer would be able to select the right injection molding pressure limit for the injection molding equipment. He could choose the right machine for himself, and we could also avoid erroneous mold design, which could lead to part rejections or insufficient part filling or lower part performances. These things could be avoided when we account for the D3 parameter. So the current method where we measure the D3 parameter, we see that the effect includes, it's a convoluted effect of pressure as well as of the high shear rates which are encountered inside the capillary rheometer instrument. So I'll talk about what exactly we are doing. So viscosity parameters at high shear rates are influenced by pressure, and we need to decouple the effects of pressure. If not, the results will be erroneous. So here we see a graph of viscosity as a function of shear rate, which is done like a representative graph measured at different isobaric conditions, wherein we have a 0 bar, which is the ambient or the ambient pressure, and then the higher pressures. We also have an actual estimated data wherein we have apparent viscosity, which is converted from the measured viscosity. So it is fitted onto the measured viscosities, and we see that it gives a good correlation. So what exactly we do to address or to find out or to determine this D3 parameter? So currently we have a method to address this effect of decoupling the shear rate from the pressure during characterization. So dynamic rheology is used to measure the viscosity at 0 pressure, and the polymer must fulfill 2 conditions. The first condition is that it should be able to follow the time temperature superposition principle, wherein you can generate complex viscosity master curves. And the second condition is that the polymer needs to follow the Cox-Merz rule, which is a simple relationship wherein we correlate the steady shear viscosity and we correlate it with the complex viscosity, which is a function of the angular frequency. So by achieving this 2 conditions of cross W of for for the model, that is the Cox-Morse rule and the TTS, we can have this D3 characterization. And I would also like to touch upon the WLF model, which mostly describes the effects of temperature on viscosity. So in an injection molding process, when the pressures are above 100 MPa, we need to account for the increased TG, the reduced free volume, and the effects of pressure. So combining the WLF and the cross model, we then see that the effects of temperature and pressure on the zero shear viscosity are accounted for, and then the effect of pressure, which leads to the shear thinning or shear thinning of the melt viscosity. So all this can be covered, and it can be correlated with the help of the Poiseuille's equation, which is generally used to measure the pressure gradient inside the capillary rheometer. So in short, what we are doing is we are accounting for the glass transition temperature, that is D2 parameter of the cross WLF model, and we are adding the D3 parameter along with the pressure component. So we are now considering both the TG with the help of the pressure dependence of TG and the glass transition temperature itself. So this is how we will cover both the factors. And then we talk about the 7-parameter cross WLF model, what each constant means. The meanings have been given on this slide. And then we have this master curve, which is generated at a particular reference temperature, first different temperatures and then a reference temperature. And then we have this methodology to determine the D3 parameter, wherein we have the pressure gradient versus the average pressure. And we see that the melt viscosity is influenced by pressure. So it goes on rising continuously. So we have this counter pressure measurement device wherein we capture the influence of pressure on viscosity, and this is done at a constant shear rate of 100 per second, which is in the Newtonian region of the polymer melt. And this is applicable for the amorphous polymers as well. And then we can characterize our pressure dependence coefficient beta, which leads us to the calculation of D3 parameter, which is given in this slide here. So I would like to summarize here that the effects of pressure and shear rate can be decoupled, and then we can have our D3 parameter evaluated, which you can see that the parameters, there are some pressure independent parameters and pressure dependent parameters, and we can arrive at the 7 parameters of the cross WLF model and provide a more complete data in order to characterize the CAE predicted injection pressures and the actual injection molding pressures, and we can bridge this gap by about 10%. So this is our finding, and I would like to hand over this stage now to Ashwin to explain the further molding validation studies. Thank you.
Thank you, Aditi. Very nice.
Thank you, Aditi. Just a quick mic check here. I hope everything is working fine. My name
Sounds
is Ashwin.
good, Ashwin.
I'm an application development engineer in SABIC Specialties business, focusing on part design, tool engineering, and the molding process engineer. Today, I'm going to demonstrate the molding process here, which from where we took the boundary conditions into the simulation environment and try to understand how does it correlate. And helping me today is my colleague here, Senthil, who is expert in the injection molding process, and he's be helping me in molding today. So today we are molding Ultem 1000, which is one of our product from high heat portfolio, which can retain its mechanical properties even at high temperature. So let's quickly jump into what's happening here in our lab, right? So to understand this molding process, we have come up with a representative design of the part. That's what I'm holding here in my hands today. So this is a kind of a boxy shape with one side open, as you can see here. And we have intentionally designed some flow restrictions to understand how does the viscosity of the resin influence the filling pattern because of these restrictions. And this is about a uniform 2.5 mm thick part with about 220 by 160 kind of a length. And to mold this part, we are using an edge gate kind of a scenario here, which is basically a combination of hot and cold runner. And you see we have a decent edge gate with a trapezoidal shape of runner with a small cold sprue. which is fed by the hot runner, right? So, and another important thing, what I want to highlight while we are developing the tool for this design, we have given a lot of emphasis to make sure that the part forming surfaces in the tool are maintained at a very constant temperature, right? So for that, we engineered the cooling channels in such a way that the temperature variation between the two halves of the mold and also even at the same side of the mold is of less than 1 degree variation between them, right? So for that, you can just look at the screen, the small screenshot there. So there are baffle coolings within the core, and surrounding the core is another cooling channel. And on the cavity side, there are additional 2 cooling channels which are trying to maintain this temperature altogether. And another important thing I want to highlight here is maintaining the temperature at the hot runner. So we have a separate cooling channel designed in the tool to maintain the steel close to the hot runner at a nominal temperature, and we connected it to the separate MTC, which I'm going to show you in some time. This is really helping us to make sure that the temperature distribution is uniform in all of the mold. So with this, let me quickly show you how the tool looks like here. As you can see, the molding is happening here, and we're going to interrupt it to just show you how the tool design is. While we are finishing with the short cycle there, I want to highlight another feature where we have instrumentation designed in the tool to understand how does the pressure changes happening. Now for that, we have 4 pressure transducers in the tool. One of it is at the runner, the one which is close to the gate, one at the middle of the part, and one is close to the end of the fill. So let's quickly check out the tool. How does it look like? So this is the tool here, team. So this is a conventional 2-plate mold with the core on the moving side and the cavity on the fixed side of the part. And this is how the part is ejected from the cavity side. And and I want to highlight the 4 pressure transducers which are on the cavity side here on the surface, monitoring the pressure. How is it varying? Now, this gives us a lot more insights onto the molding process to understand how does the pressure variation is as it is filling, what's the compressibility of the material. It will also help us in understanding how are the different regions shrinking. This influence is given by how the pressure profile is decaying inside the mold, right? So that is something which again I'll demonstrate in some time. So this is the tool structure what we have here, and let's start the molding process, and I'm going to introduce the molding infrastructure setup from here now. So before I start off with the understanding the process, I just want to introduce the molding infrastructure here. What I have here is a Sumitomo make an all-electric, high-speed, high-pressure machine. It's on the clamping side, it has 130 tons, which it can deliver. And on the injection side, it's a 36-dia screw with about 140 grams of short weight. It can achieve a screw speeds of 360 mm per second, and the pressures can go up to 290 megapascals on this unit. Now, supporting this molding machine, there are a lot of auxiliaries which are equally important to get this a uniform, streamlined kind of a robust molding process. So I'll quickly try to show you what are the auxiliaries which are going into molding this sample here. So this are the MTC setup, what I have. As I highlighted, there are 2 different MTCs which we are using today. One of it to maintain the temperatures on the core and the cavity side. And I want to highlight another important feature here. We have not looped in any of the cooling channels between the in and out. What we try to do is we use the manifold to make sure that the equal flow rates are going into each of these cooling channels. and another MTC, which is whole and solely used to control the temperatures near the hot tip. Now that's what we are using a separate MTC here. And for molding Ultem, what we are using here is 150 degrees C to set it up as a mold temperature, and about 110 to control the hot runner region close to it. Now, this is the dryer system what we have. It's a completely closed loop dehumidifier kind of a dryer. We have been pre-drying for about 150 degree C for Ultem for about 4 hours. And as you can see, these are about 50 liters kind of a capacity. And I want to highlight the feature here. From the dryer to the machine hopper, it's a completely closed loop system wherein the material is automatically conveyed into the hopper, and to have this streamlined, non-stop auto cycle kind of a molding process. Now, let's quickly go back to understand the other setup which we have here. I want to highlight another important unit. What we have here is the Kistler pressure acquisition system, pressure transducer acquisition system. Basically, what we have here is the curves which are basically monitoring the pressure inside the cavity and reporting it out, right? So let's look at the molding cycle. How does the pressure changes when we are reviewing the pressure profiles from the molding machine itself? So now to arrive at a robust molding process, we have employed scientific molding techniques. I'll try to take you through some of these steps of how did we arrive at this process optimization to make sure that the assumptions from the simulation are really being correlated in this aspect here. I'll start off with the temperatures. We start to set the barrel temperatures as recommended in the data sheet in the mid-range. The same goes for the mold, where we set it for the mid-range of the data sheet recommended values. As you can see, it's 390 set in this barrel profile here. And to highlight the filling part of it, right? So we have employed the in-mold rheology part of it to understand what are the optimum, what is optimum fill time or the fill rate with which we want to fill the part. Now in this, we fix the screw start and the screw end position, and we keep changing the screw speed and monitor how the pressure is changing. And as you can see, that is a typical curve of from this boundary system of the design and the tool. You get something of a similar curve what you see there, and we pick the lowest range where the variation is not much influenced by any of the changes in the environment. So with that, we fixed about 35 mm per second as a screw speed, and that is resulting about 2.2 seconds kind of a fill time for this kind of a part. And for the packing stage, what we try to do is basically understand the gate freeze and make sure that we have enough window there to pack the part out. Now in this case, the gate freeze happens is about 5 seconds of packing time, and the packing pressure is something which we estimate in the basis of a cosmetic processing window. We don't want to be at a higher side of the pressures wherein we are flashing the tool, and we also don't want to be on the lower side wherein we are seeing a waviness or not a good surface replication from the cavity. So from that, we see about 110 megapascals is what we have set it as a holding. And another thing I want to highlight on the dosing stage, the refill stage, what you call as the back pressure and the screw RPM is also something which is really important to make sure that there are not many variations happening in the melt temperature when it's prepared in the barrel. So for that, we are using the 50 RPM kind of a screw speed with the 2.2 megapascals of a back pressure. That is resulting about 21 seconds of a dosing time, which is still under our control limit of cooling time. And also I'm getting an additional 15 seconds for the dwell time where the melt temperature actually stabilizes, right? So with these boundary conditions, let's look at what is the output we usually monitor. So some of the typical outputs, what we monitor is the fill time, the cushion, and the refill time, and also the peak pressure. For this molding process, let's quickly look at what are the pressure curves we are seeing here. Right. So what you see here on the screen is the pressure curve, which is a result of the boundary conditions what we have used in the molding process. And this is the pressure curve, what you see Peter comparing in simulations for one of the Ultim grades, what we are molding today. Now, as a response to this, what we have additionally is from the pressure acquisition system from the crystalline. So these are the pressures from 4 different locations in the tool. One is at the runner, close to the gate, mid, and end of the fill. Now, these is also something which Peter has used in his simulation to understand how the pressure correlation is between the analysis, right? So with this kind of an optimization and having a robust kind of a process established, and we make sure that it is being run for a minimum of 30 shots or about 30 minutes to ensure that the process is stabilized. All the process outputs are within consistent range of what we're expecting. And that is where we take the data, we extract the data from these molding machines, the pressure curve from the machine, the sensor curve from the crystal acquisition unit. And that's where these data goes to the simulation and understand the correlations with the material data characterized by our experts here and the molding process used from this setup. Now let's look at how does the simulation results look like with the SolidWorks system. So Peter, it's all up to you now.
Okay, guys, can you hear me?
Yes, we can hear you.
Yes, we can hear.
Okay, very good. Well, Subhranshu, Aditi, Ashwin, thank you for that. Can you see my screen? Okay. Andy, can you see my screen?
Yes, Peter, I can see your screen.
Geez, I've got to tell you, so for all the attendees, I think some of you have heard this is the first time we have done such a webinar with a distinguished partner such as SABIC Specialties. And again, Subhranshu, Aditi, Ashwin, thank you for giving us a glimpse of what I can only describe as injection molding heaven. As a plastics guy, what you're doing is truly amazing. And so now, as Ashwin said, in fact, if we look at everything that SABIC is doing here, not from the very beginnings of when they're developing formulating and developing a new material in the first place, and then once they have their grades that they're going to commercialize, the very rigorous steps that they take to test and characterize the materials, as Aditi covered, and especially when it comes to a viscosity coefficient such as the D3, when you have these highly pressure-dependent viscosity materials where it's not exactly a simple or easy task to simulate how such materials will flow into an injection mold. And then, okay, so they cover all of their material testing, and then they go to an injection molding machine to internally make sure that the material data that they're generating and what they're seeing at the injection molding machine correlates. So now we come along and we say, hey, guys, could we, SABIC, could we please get a hold of your material data so that we can run it through our software to see if we're also getting these good correlations between the real world molding results and the simulation. And so I'll just give you a brief glimpse into the window of what we did, which is this now quite a long-running validation study, which, by the way, we also intend to expand upon in the future. So simple objective here for this validation project. Of course, we're using the mold and the geometry that Ashwin was showing, and we just want to correlate SolidWorks plastic simulation results with the empirical evidence coming from SABIC's injection molding laboratory, and this is to validate both solver and material data accuracy. Again, SABIC supplies us with pretty much everything that we need in terms of the part geometry, the material data, the viscosity curves, the PVT, the curves, the thermal properties, the mechanical properties, as well as the injection molding process parameters that they're measuring and tracking from the machine. We run our SOLIDWORKS plastic simulations, and then we simply compare the results. Some of the steps that we take behind the scenes, you saw Ashwin describing the part geometry. You have the box cavity with a fan gate fed by a cold runner system. That cold runner system is fed by a hot runner system. And for this validation study, we actually model all the way back to the nozzle of the injection molding machine, which is a perfectly valid thing to do. I mean, if you think about it, this is basically where flow starts. And by modeling all the way back to the nozzle of the injection molding machine, you can just get, let's say, finer or more granular detail in your correlations. Of course, we're taking all the material data, which Aditi covered. We're relying on SABIC for that material data. We then take their model geometry, generate our mesh model inside of SOLIDWORKS plastics. In this case, we also did a venting analysis where we included the vent locations just in case they had a significant effect on the pressures generated inside the mold cavity. We take the process parameters that are coming from SABIC's injection molding machine in their laboratory. We translate that into the simulation process parameters that we use to set up the analysis. Here you can just see the hot runner and the mold temperature settings that were used for this validation study. And now we can start to dig into some results. And we did run this for two different materials, Ultem 1010 and Ultem 1000. Today, in the interest of time, I'm just going to present the results for Ultem 1010, but rest assured that we got equally good results for the Ultem 1000. Now, in terms of injection molding simulation, the first plot that we always look at after we run any analysis is the animated plot of the filling time. And this is, in some respects, kind of a simple sanity check. You might say that this geometry appears to be relatively simple. I would say that's not really so much the case. In fact, this part, SABIC will tell you, has been designed to pick up some very fine detail as the plastic melt flows through the cavity. But we look at the animated filling time plot, and overall, we just instinctively say, you know what? Everything looks pretty good here. We're seeing a filling pattern which we would expect to achieve from this type of geometry. This hot runner into a cold runner into the box mold geometry. But now we can start to take a little bit of a deeper look at. We might say, okay, maybe we're getting the filling pattern right, but are we getting everything else right? And one of the first things that we look at with this validation model are the weld line predictions. As I said, this part was designed with validation in mind. And what you can see here is what I would humbly say is outstanding weld line prediction. So all of these through holes that you see here, we're picking up the weld line prediction on all of them. And some might look at that and say, well, that's a relatively simple and easy thing to do. I would say not so much, because without going into all the detail of predicting weld lines, it's depending on how you tune your solver, it's very easy to overpredict weld lines or underpredict weld lines. Sometimes very difficult to tune your solver to the point where you can just accurately pick up every weld line that's physically occurring, and then also avoiding a lot of noise that might otherwise occur. Okay, and now where sometimes I say this is where the rubber really hits the road. It's one of my favorite correlations to make in these types of studies. It's the short shot series comparison. Now, what you're seeing here on the right-hand side of this slide are actual photographs of parts as they come out of the mold. Now, this, if you're not familiar with short shot series, this can be somewhat of an inexact science because let's say as we're looking at these short shots here, maybe the first short shot at the top is I don't know, not even 5% filled, and maybe the second one is 5 to 10% filled, and the third one is 10 to 15 or 18% filled, or something like that. Well, you know, when you're actually molding these parts in these short shots, it's not possible to just stop the machine at 10% filled. And the other thing that you have to think about is that as this melted material flows into the mold cavity, it's under compression, and when you stop, when you release the pressure on the system, the material can actually continue to flow as it decompresses a little bit. So that's all to say that it's not exactly easy. You know, here we see the finished pictures. You might think, oh, it's very easy to create these short shots. Not so much. And then when we, what's not quite as difficult is then matching up the filling patterns from the simulation predictions to the physical short shots. And so this is now what you see here. The reason why I like this so much is because there is essentially no denying what is happening on the right-hand side of the screen here. And as we look at these simulation predictions on the left-hand side, you can get a really good idea of how well the software is predicting the progression of the melt flow front as it flows through the cavity. So here you see from top to bottom, we like these results. These are pretty good results. As we go further into the cavity, in a lot of respects, we're starting to look at finer and finer detail here. You can see that the simulation, the filling animation or the filling pattern on the left-hand side is picking up the the overall profile of the flow front as it flows through the cavity, as well as some of the phenomena that are starting to occur as material is progressing around the core or cavity features, which are generating all of these through holes and the weld lines. And we take it further through to the end, and you can see, I would say from 30,000 feet, you look at the filling pattern, the predicted filling pattern versus the short shot filling pattern. We basically don't, we don't believe there's any better correlation than this, kind of due to the nature of generating these short shots in the first place, and then, how we can look at this from a simulation standpoint. So, looking at these results, filling animation looks good. Weld line predictions look good. We look at the short shot series. We're happy with everything that we see here. And now, kind of the true test, especially based on, a lot of what SABIC has been presenting today, is how well are we predicting the pressure in the system? Because without going into all of the detail, I think if you've been involved in injection molding for any length of time, you know that being able to accurately predict the injection pressure requirements and the injection pressure distributions and the pressure drop through the system, as the melt flows through the nozzle of the injection molding machine, in this case through the hot runner system, through the cold runner system, through the gate and into the mold cavity. If you can accurately predict pressures, you can get almost everything else right. And by everything else, I mean shear stress, volumetric shrinkage, and then maybe ultimately molded part warpage. So here we see an overall injection pressure prediction of just shy of 82 megapascals in the system, and this is at the inlet point, basically at the beginning of the nozzle of the injection molding machine. But this is the kind of the final result of this particular validation study, which again we do intend to take this further and deeper into the process with SABIC in the future. You saw a lot of that information that Aditi was presenting on the lengths that SABIC goes through to make sure that they are number one, measuring for this D3 viscosity parameter, and number two, that it's accurate. So in fact, I'm the first to admit, when we first started running this validation study, you see three curves on this slide here. The green curve, that's the value which is provided to us by SABIC coming from the injection molding machine. But the first curve to take a look at is the what might appear to be an orange curve on this chart, where the peak pressure we predicted was just shy of 50 megapascals. Now, the way I describe this problem, and by the way, when we first ran this validation study, it was what I call a blind taste test. So SABIC gives us the part geometry, they give us the material data, they give us the injection molding process parameters. We have to run all of that through our software and then present the results back to SABIC. And we say, hey, kind of just like I'm doing here this morning or this afternoon, here's our filling pattern, here's the weld line predictions, here's our pressure prediction, here's our pressure curves. And so when we first did this, SABIC said, okay, very nice job, but we gave you a problem of 2 plus 2, but the answer we got was 3. And what I mean by that is, as you can see here, we were under predicting the peak injection pressure by somewhere in the range of 25% or so. It turns out that, in fact, as Aditi mentioned regarding material data, in these, especially for these pressure-dependent viscosity materials, oftentimes the D3 viscosity parameter is simply not there. It's not tested for or provided, or even if it is there, the injection molding simulation software may assume, let's say, something different. Now, I'll admit, in our case, we had the D3 parameter programmed into our software, but let's say there was a switch which was off, we were just always assuming that D3 was 0. We did a little bit of work to our solver. We let's say we turned the D3 coefficient back on. We had to do some some work and some tuning to get it just right. And when we finally finished, the result we got was the blue curve. So what you're seeing there is green curve, experimental measured value, orange curve. This is SOLIDWORKS plastic solver without taking into account the D3 pressure dependent viscosity, and the blue curve is the SOLIDWORKS plastic solver with taking D3 pressure dependent viscosity into account. So, based on, again, all the results that we look at here today, the filling pattern, the weld line predictions, the short shot series comparison, and now the pressure prediction and the pressure curve, we're all very happy with these results. So the key takeaway regarding the validation study is that for the scope of this phase of the validation study, SOLIDWORKS plastic simulation results exhibited outstanding correlation with the SABIC box model real-world molding results, including, again, the injection pressure traces, the filling patterns and short shot series comparisons, and the weld line location predictions. So to summarize, everything that we've talked about today, I think you can now see that we work very closely with SABIC Specialties to ensure that our mutual customers have access to trusted, accurate, and validated CAD simulation material data. In fact, since we've been working with SABIC, I believe we have added somewhere between 300 and 400 SABIC sourced and validated materials to the SOLIDWORKS plastics and 3D Experience plastics material databases. So basically, if you go into that software today and pick a SABIC specialties material, you can have full confidence that that's basically the best data that we can generate, and I say that even exists on the planet. I think you've seen just the brief glimpse into their state-of-the-art injection molding laboratory. SABIC spares no expense regarding the testing and validation of their material data, which is done in world-class facilities. I think this is, not something to be taken lightly. It's a behind-the-scenes look that, the average person in our space doesn't get to see. But if you ever go into a material database and the material that you need is not there, maybe now you have some idea of what it takes behind the scenes to test and generate that material data in the first place. Basically, not easy and not inexpensive. And then finally, the combination of SABIC Specialties material data and SOLIDWORKS plastic solvers gives you simulation results that you can rely on. And this is one of our main goals or objectives here, is to make sure that our mutual customers are comfortable and confident in running the simulations, so that the ultimate goal is so that you, our customers, can design and optimize better parts that are more sustainable and that align with the goals and objectives of a plastics circular economy. And then finally, please do feel free to reach out directly to SABIC if you're using SABIC materials today. If you're considering using SABIC materials, please contact these guys. Visit their material finder webpage. They have outstanding resources to help you maybe determine what SABIC material is best going to meet the application requirements for your products. And then they can also help you in many, many, many other ways. And what I always love about these kinds of engagements is that, when it comes to SABIC materials, there's no one better to get in touch with than SABIC directly, so that they can help you, better select your materials in the first place, and then optimize your products based on their material properties. So with that, again, I would thank everyone for their participation today, especially our distinguished guest speakers from SABIC, Subhranshu, Aditi, Ashwin. We sincerely appreciate your support and your participation today, and we look forward to doing many more of these in the future. I think I've already gotten some feedback that says this was probably our best plastics webinar ever, and I think I might have to agree with that. So with that, I'll open it up to questions, and for the attendees, you can please feel free to type your questions into the Q&A panel, or perhaps the chat panel, whichever one works for you, and we'll try to address as many as we can live here. And any questions that we don't get to live, we will certainly follow up with you after the fact.
Thanks, Peter. Maybe some questions that I already answered during the webinar regarding the recording. So currently the webinar is recorded. I will make sure that it's in the follow-up email that you will receive on the coming Monday. I will put the link there to the streaming, so you can forward this to colleagues that might be interested in this topic, or for you to review the recorded session.
Okay, sehr gut. Vielen Dank. Andy, do you see any questions?
So I don't see any unanswered question right now.
Okay.
There was just one coming in. Yep.
Stop my share. And Subhranshu.
Yeah, I can see one question, right, Peter? There is a question which can you hear me?
Yes. Yes.
Okay. Which differences you may highlight between die-cast simulation of metals and injection process from feeling point of view? Ashwin? Okay, I think There is another question which Peter, you can take it. Is it possible to add the D3 to the older releases?
Yep. I see that. Holger, I will check into that with the R&D team and let you know. Right now, I don't know for sure if it's possible or not. But thank you for bringing up the point. And Subhranshu, Ashwin, Aditi, I don't know if there's just anything else that you wanted to add. Again, we sincerely appreciate your participation and your content today. I think what you did was amazing. And I would just say thank you for allowing us to view a little slice of injection molding heaven.
No, thank you to you and your team also, and thanks to our team here in SABIC. I think it was a it was a good webinar that hopefully helped our mutual customers to get an idea of what SABIC and Dassault together can provide to make their injection molding really the trusted simulation tool to to rely on. Like Peter mentioned, if anyone has any more questions, feel free to contact us. We have the the SABIC Metal Finder. You can go and register there. You can get all the information, and if you still need any more information, there are contact details on the portal, which you can contact us through that. I can also type the contact detail here. It's material-data at sabic-specialties.com. So please feel free to contact us for any of your needs. Yeah,
okay, very good. Okay, we got it. Andy, I think if you don't see any more questions.
So there are
okay.
additional questions. So maybe we start with the last one. So the question is, for generic materials such as PC plus ABS, will one also see an improvement in results? So I guess as those materials does not exist in reality for a generic material.
Yeah, I think I can speak to that, Andy. So yeah, when it comes to generic, the reason why we have generic materials in our database, as well as other software providers, you probably know have the same. It's basically because there are, I would guess, tens of thousands of commercial grades of plastics available in the world today. But of course, you've been given a brief glimpse, today into what goes into the expense and the rigor with testing and characterizing plastics materials. So basically, the long story short is that material manufacturers, even no matter how big they are, often cannot justify testing and characterizing all of the materials in their material catalog or material library. And this is essentially why we have generic materials. Now, our approach for generic materials is for a polycarbonate, for example, or a PCABS. We try to, let's say we try to pick what you might call or refer to as a middle of the road solution. So if it's a polycarbonate, maybe not a very a high viscosity polycarbonate or very low viscosity polycarbonate, but something that's kind of in the middle of the road that will get you into the approximate range of what you would expect among within the polycarbonate family. And so the viscosity curves or the viscosity coefficients that we would include, the PVT coefficients, the thermal properties, and the mechanical properties are based on that for all of the generic materials in our database. And for us, we have a generic polycarbonate, a generic PCABS, a generic ABS, basically one generic material for each family. Now, depending on the aim of your analysis or the goal of your simulation, I guess Subhranshu will tell you, if you want the most accurate results possible, one of the first things that you must have is grade-specific material data. Otherwise, your pressure prediction may not match exactly what you get at the molding machine. and then from there, of course, if the pressure doesn't match, then shear stress predictions won't match up, volumetric shrinkage predictions won't match up, and ultimately you may not be able to accurately predict molded part warpage if that were, if that were a concern. In the case of SABIC, like I said, we've added since we've been collaborating with SABIC, I think somewhere between 300 to 400 of their materials to our material database. So, our goal is to have every SABIC specialty material which has been tested and characterized either immediately available in our database or available upon request from SABIC. And of course, the same would apply with any other material you use. So I hope that answers that question. I see another question. Do we have a material characterization laboratory at Dassault Systèmes? That the short answer is no. We do not get involved in material testing. You can consider us more software, software providers, and maybe adding some plastics domain expertise. But we rely 100% on partners such as SABIC Specialties for the best data that we can get our hands on. Basically, I think as you've seen today, we get the most trusted, the most accurate, and the most up-to-date data that we can get by just engaging directly with SABIC.
Perfect. Thanks,
Okay,
Peter.
and I don't see any more questions. And again, I would just like to thank everyone for attending this webinar today. We hope you found the content useful and informative, and we're looking forward to many more with SABIC and our distinguished guest speakers in the future.
Thank you. Bye-bye.
Bye, everyone.